everyone, welcome back to our lecture video today. So the topic of discussion today will be frequency response. Um, as you all know, our amplifier actually respond differently at different range of frequency. What happened in previous lecture is we just assumed that our amplifier is at an optimal frequency that's not too high, not too low, to get the specific gain that we wish. However, in practice, due to a lot of capacitor effect, our amplifier will respond differently at different frequency range. So today we will learn a little bit deeper regarding the response of our amplifier at different range of frequency. Also, we will study how to use a graphical tool called Bode Plot to see how the amplifier respond in different frequency. So let's get to this. So in here we have a typical gain versus frequency plot. Um, as you can see, on amplifier gain factors are actually a function of, the signal frequency. In this specific plot in here, in the x-axis, you can see the frequency is plotted in log scale. The y-axis, the gain is plotted actually also in log scale. It's just expressed in the unit of decibel or dB. So as we noticed before, as I say before, up to this point, we all assume the signal frequency is usually high enough so that the coupling bypass capacitor can be treated as short circuit. And what is coupling capacitor? Please look at the circuit below. You can see a capacitor that running into your base, for example. So if the signal is high enough, that capacitor is shorted out as short circuit. But we also assume that our frequency is low enough so that the parasitic low and transistor capacitance, that means all of the capacitance the internal capacitance inside our transistor, can be treated as open circuit. That means the frequency is low enough that it doesn't affect the capacitance of those internal capacitor doesn't show up. So basically in this plot here we have three main regions. We have first the low frequency region, we have the high frequency region, then we have the mid-band region. Low frequency region is where you have your frequency is lower than FL, which is your, so we have the low frequency region, so everything less, all the frequency less than FL. So in this region in here, basically the frequency is too low, so this capacitor now is acting as this open circuit, okay, or it's not shorted as a short circuit anymore. Therefore, you can basically you can have the how can I say, you can have the gain reduced as the frequency reduced at the high frequency, so everything above this FH, okay, you can have the frequency reduced as you increase your frequency. The gain reduced as you increase the frequency. And that is because when your frequency is high enough, those internal capacitor inside won't act as open circuit anymore. It will start acting at like short circuit and reducing your gain. Therefore, there's a middle region called midband. The midband region or the midband range is where the coupling and the bypass capacitor act as short circuit, and the internal capacitance act as open circuit. So in this region, your gain is almost a constant. Another one thing to notice is the bandwidth of the amplifier is defined as this width here. So just use FH minus for FL, okay, and you can have this whole thing to be bandwidth. One more example is for an audio amplifier. The signal frequency is for like an example audio amplifier. A signal frequency is in the range of 20 Hz to 20 kHz, for example. So it needs to be equally amplified equally, so that it can produce the sound as accurate as possible. So in the design of a good audio amplifier, the frequency FL must be designed to be less than 20 Hz, and the frequency FH need to be designed to be greater than 20 kHz. And the reason why is, as you can see in this plot, even though we say FL and FH is the limit, is kind of the range of our midband, but actually at the edge of FL or at the edge of FH, the gain is 3 dB lower than midband. So sometime when you make some audio amplifier, you need to extend this part a little bit more to have equal amplification effect on the whole desired range that you want. So next step, let's go through some typical example of system transfer function. So we have this circuit in here, and our goal is to derive the transfer function for this basic first order amplifier. So first of all, what is the transfer function? Is technically it's a frequency dependent function of let's say voltage, output voltage over input voltage, or in general an output terms over an input terms. So let's figure out so if you use the voltage divider rule, okay, if you apply your voltage divider rule, you can have the relationship between your output voltage and input voltage to be Rp, this resistance here, over the sum of the impedance, the total impedance of Rs, plus impedance of this capacitor, plus
resistance or impedance of Rp. So you have these two plus 1 over, and usually right here you have J omega Cs, but as I say in here, just for the sake of convenience, we can, instead of working with the frequency domain, we can move to work with the S domain by replacing J omega with a variable S. So now every time you see S, it will be equal to J omega. And omega is angular frequency. So in terms of regular frequency that you measure in hertz, omega will be equal to 2 pi f. So next, let's move on. You can next try, rewrite the equation as this form. And what you want to do next is now you want to group out this term r pi over rs over plus rp over rs plus rp, and that is basically the sum, like basically your voltage divider rule. Assuming this capacitor is short circuit, okay, so you want to factor out that term. Now in this form of VO over VI, you have two major terms. The first term you have is this big term Rp over Rs plus Rp. You can call this one, this term to be K. Next is this whole term of Rs plus Rp, then multiply for Cs. This is called a time constant, and this time constant tau s is basically the time constant of this whole amplifier circuit in here. Therefore, now we can write our equation as K multiplied by S tau over 1 plus S tau. So now we can write our transfer function as T in terms of J omega, or in other words will be T in terms of S, equal to K multiplied by S over 1 over tau plus S. And that whole thing can be written as S over omega naught plus S. Some of you may ask, what is omega naught? Omega naught is equal to 1 over tau S. Okay, so if tau is a time constant, so the unit of tau is time, right? For example, seconds. So 1 over tau will have the unit of frequency. Therefore, this term even is also a constant, and you would call it a corner frequency. And later on, when we go through Bode Plot, I will explain why we call it corner frequency. But anyway, here is how we define K, as I said before, and our corner frequency omega naught is equal to 1 over tau. It's quite simple. So this whole thing here is a high pass filter. So some of you may ask why. So let's look at this form of the equation first. Let's assume that what happened if I have an S equal 0, or S coming close to 0. If S coming close to 0, this whole term will become 0, right? And so if this whole term becomes 0, therefore the gain of our VO over VI, or our transfer function, will become 0. However, as you increase it, and you raise S unto infinity, then the value of S here will be a lot larger than the corner frequency, right? If you increase it large enough, then at one point you can see, oh, it will be S. At one point, if our omega naught become negligible in comparison to S, then you can assume that S equal to omega naught plus S. So if SS go very large, therefore this whole term will become 1. Then your transfer function will become a constant k. So that's so you can have a result of a gain of a factor of k. So this is your high pass filter. You can have a canonical form of this high pass filter to be Ts equal k over 1 plus omega naught over s. Okay, and this circuit is called a series coupling capacitor circuit. So next we move on to a different type circuit. So in the previous circuit we have a capacitor over here, which is in series with our technically in series with our RP, the load capacitor. However, in this case, we want to have the capacitor in parallel with the load capacitor. So what do we do is what do we do to analyze is at the output node, we apply the Kirchhoff current law. Okay, so we can have this equation here. Okay, let's do some magical arrangement. You move everything on one side, VO on one side, VVI on another side. You can divide the whole term for each other. So then finally you can have the terms of VO over VI. And the same thing applies. You do the same thing, you will be able to factor out this term, RP over RS plus RP, which is voltage divider law for this one over the whole sum. Okay, you can call that term K. Another term to notice is when you have RS parallel RP, then CP. This term is called the time constant, TP. So this is the time constant of our of this amplifier circuit. So you can write down the whole function of the whole transfer function as Ts equal K multiplied by 1 over 1 plus tau s, or you can rewrite tau s in terms of omega naught, or the corner frequency. And here's 45K in corner frequency. And this one is a low pass filter. Why? When you have S go to 0, this term get cancelled out. The whole transfer function become K alone. So at a lower frequency, the gain is K. However, when you increase the frequency higher, so you increase S. So S become very, very large, for example. So as S increase, this denominator also increase. When denominator increase but numerator is constant, the value of the whole fraction decrease, right? Therefore, your gain will drop down, right? Down as you increase the frequency. Therefore, this is for low pass. It's for low frequency. It has a constant gain of K. For higher frequency, it starts losing its gain. So therefore, you can call it a low pass filter. And this circuit is called a parallel load capacitor circuit. So both of these two circuits, the high pass filter circuit and this low pass filter circuit, both of them are called first order transfer function, like first order transfer function. The reason why, or first order amplifier circuit, and the reason why is there's only one capacitor in this circuit. So I think I put a note on, so why first order? Because only contain one capacitor. Okay, so we go a little bit deeper in terms of transfer function. So there's different way to represent a transfer function. So previously we present our transfer function as S in S domain, right? You can also write your transfer function in terms of frequency domain as omega or as f. It's up to you. So if H omega is a frequency dependent ratio of output phasor y omega to the input phasor x omega, we can have 4 different possibilities to present this transfer function H omega. We can present it as a voltage gain, as we showed before, when we have the output voltage divided by the input voltage. We can also represent the current gain with this transfer function. So we have to we have to use I/O, the output current, divided by the input current, or we can use that to represent the transfer impedance, so V over I, or transfer admittance, which is I over V. Okay, there's a long arrow here. And so in the transfer function, you usually have 2 main factors. First, you have a magnitude, then you have phase. Some of you ask why, because remember, it's technically, if I represent it in S, usually the transfer function have a J component in it. That means there's a real and there's an imaginary factor in your mathematical view right now. Therefore, the transfer function usually is have a magnitude, is when you take off the real component, and let's have a phase, like contributed by the imaginary component. Okay, so if you assume if from this, you can also represent your transfer function as a fraction. So you have numerator in terms of so you can represent this either in frequency domain or S domains. You can also have denominator. Okay, so when you write in this form, you have to assume that all of the common factors in the numerator and denominator have been cancelled out, so you have to do the math by yourself. Okay, so if you make the numerator equal to 0 and you solve for the solution, and it's called roots. Okay, so the root of the numerator is called zeros, and the zeros are basically the solution of S at Z1, Z2, Z3. If you do the same thing for the denominator, the root of the denominator is called poles. Okay, the poles are at P1, P2, P3. Some of you are asking me what is Z1, Z2, Z3, P1, P2, P3. So I can show you in here. This is a generic transfer function, TS, or I can write that in the frequency domain, which is H omega. This can be equal to, okay, you can factoring out on a of your constant as a K. Then you can write your numerator like this. So technically, your numerator will have, let's say your numerator can have several solutions depending on the order of your numerator. The first order only have 1 solution. Second order we have 2 solutions, and n number of nth order will have n number of solutions. So each solution for the numerator is called zeros, and each solution for the denominator is called poles. So next, let's find the Bode plot for our high-pass filter network. So I put the high-pass filter circuit in here, and this is the canonical form for our transfer function. So what I do next is I actually multiply both numerator and denominator for s over omega naught. Then I substitute j omega equal s, or s equal j omega. Okay. So if you see in this terms here, I have omega, right? I can also represent omega, or aka our angular frequency, as regular frequency in terms of 2 pi. Okay, so omega equal to 2 pi f, and omega naught equal to 2 pi f naught. So this is our corner angular frequency. This is corner frequency. Okay. So I write everything as f right now. It looks a little bit complicated, but if you take a quick look, you can see that this is technically 2 pi over 2 pi, so you can cancel out those 2 pi. Okay, so if you compare this term and this term, technically you just take the omega out and put the f in. Pretty easy, huh? So now what we want to do is we want to understand the magnitude of our transfer function. Remember, as I said before, transfer function have two components, magnitude and phase. So now we want to study the magnitude. So we take the magnitude of this complex number function in here. We would have basically k is a real number, so it just come out the same. This whole fraction here, the numerator become f multiplied by, or f over f naught. Then the denominator is the square root of 1 plus f over f naught square. Okay, so next what we want to do is we want to represent the magnitude in terms of dp, which is decibel. Okay, so in order to do that, you want to take 20 multiplied by, actually first take logarithm of 10 for this whole factor, this whole term, then multiply them by 20. So you do that, they put this whole thing in this bracket. Okay, so what next is, because it's logarithmic, right? So if it's multiply, you can do like, if you have log a multiplied by b, then you can have is equal to log a plus log b. So I use that rule. So I can have 20 log 10k, so this k put here, plus, okay, plus the numerator put in here, minus, why minus, is because this term is in the denominator. So if you divide something in the log bracket, you have to use a minus sign. So minus 20 log 10, and put the whole numerator in here, I mean denominator, I'm sorry. Okay, so now I just write, so now I written now the whole transfer, the whole magnitude expression of the transfer function again. It has 3 terms, right? So in order to have a plot that represents the magnitude of our transfer function over different frequency, what you want to do is, now you have different terms of the magnitude, so you can plot out the 3 terms, then add them together. Okay, so let's start with the first term first. So in the first term, you have 20 log 10 of k. Okay, k is a constant because our function is an f dependent or frequency dependent function. So k is a constant. Therefore, the whole magnitude, like the whole plot would be a flat line. Some of you may ask, why is it below 0? The answer is because we have Rp over Rp plus Rs. So this fraction is less than 1. So if you take a log of something less than 1, you have a negative number. If you take a log of 1, you have 0. If you take a log of something larger than 1, you have a positive number. Okay? So next we want to take care of the second terms here. The second term technically is f multiplied by a constant inside the log bracket. So your result will be technically a linear relationship, because a linear relationship. So since you have only one f terms here, okay. The question is now, what is the slope? This slope is 6 dp over 1 octave, or 20 dp over a decade. So octave means frequency increased by a factor of 2. So let's say 2 hertz, 4 hertz, 8 hertz, something like that. Then 20 dp over a decade, and decade means frequency increased by a factor of 10. So 10 hertz, 100 hertz, what's that? 10 hertz, 100 hertz, 100, like 1000 hertz, something like that. Look at here. You have so you can see this linear line equal to 0 at one point, and that point is pretty important. Okay, if you look at this terms, so what if f equal f naught? If f equal f naught, then this whole term inside become f naught over f naught equal 1. So this whole thing become log of 1. As I say, log of 1 equal 0. So this is when your linear line cross, this is when your linear line cross the x-axis, it becomes 0. So at the corner frequency, the second term becomes 0. So for the third term, when the frequency is a lot less than the corner frequency, the value of the transfer function is basically 0 dp. Okay, because when f is very small, okay, this term will become 1. Therefore, it will become like the whole log term becomes 0. So when this term is very small, 1 is a lot larger than them. Okay, so this whole term becomes 0. So if you do the math and plug in everything, okay, if you do the math, plug in f naught, cancel out the term. So technically, if you plug in f naught in here, what you have is you have a square root of 2 inside, right? You finish off that math, you actually calculate that at f equal f naught, your function become negative 3 dp now. Okay, so at f equal f naught, the transfer function become 3 dp less than 0. But as you go further than the corner frequency, like a lot further, then you have let's say a negative slope, and this negative slope is negative 20 dp per decade. So now if you add the 3 terms together, you can have what is called the Bode plot. I mean, you add the 3 terms and you also provide some approximation. You can have something called a Bode plot. Okay, so if you have the frequency is a lot larger than your corner frequency, the second terms and the third term, since it have the same slope, but one is positive, one is negative, so effectively they will cancel out each other. They will cancel each other out. If you have the frequency is a lot less than your corner frequency, a large negative dp value from the second term will be the domination factor. But also, if you remember the third term, the curve, it was a curve, right? It's not a line. However, for the sake of convenience, what different in Bode plot is you actually have asymptotic approximation. So since this line and this line are linear, so you can have a linear approximation toward the corner frequency, so that you can toward the corner frequency, so that you can easily draw like an approximation plot. If you want to know what is the actual gain at the corner frequency, it's actually the k factor negative, like minus by 3dp, and this point is 3dp below this pink line up here. So how about the phase component of our transfer function? So first, let's see how can we express a complex number in terms of magnitude and phase. So if you need more help with complex number, I attach a document to review complex number in the CAN-BEST module. So please review that if you need to. But in here, as you can see, typical complex number have a real and an imaginary component. So if you want to plot this complex number a plus jb, you usually trace in the real component, then you plot out a. Okay, so you plot out a, then you trace in the imaginary component and you plot out b. So you have your number plotted in the complex number field in here, with the real component and the imaginary component. Another way to express a complex number is in terms of magnitude and phase. So magnitude is when you draw a vector from the origin to the point of interest, then you measure the length of this vector or the magnitude of this vector. So if you apply Pythagorean, you can have this length equal to square root of a squared plus b squared. The phase is basically this angle, which is theta, equal to arctan or inverse tan of b over a, or this b over a. So by using trigonometry, you can figure out the phase. So let's rewrite our transfer function. I just write again the transfer function that we have here with 2 pi cancel, like a 2 pi up and down cancel. So in here you can see we have 3 terms, right? We have the first term here, the numerator term and the denominator terms. The first term k, you can actually express that as a complex number, even though you know that it only have a real component, doesn't have imaginary component, but it's complex number term. This complex number can be expressed as this. So this is the magnitude of k multiplied for the phase component of k, e to the j theta 1. You do the same thing with the numerator and the denominator. So you put the numerator here to take out the magnitude, multiply for e to the j theta 2, and this is the phase of the second term. Likewise, do that for the first term, and you have the phase of the third term. So if I call this to be k1, I call this whole thing to be k2, and this to be k3, then I can write this whole thing to be basically one complex number multiplied by another complex number divided by another complex number. So technically, I can group all of the magnitude together and all of the phase component together. So now the effective magnitude of this transfer function is k1, k2 over k3, while the phase component of this complex number is, or the total phase of this transfer function is theta 1 plus theta 2 minus theta 3. So let's examine the first term. The first term we have is theta 1 equals 0, and the reason is k only have real component. Therefore, theta 1 equals to 0 degree. So in the opposite way, theta 2 only have the second term only have imaginary component. Therefore, it's only on this axis, right? So the angle is of course 90 degrees no matter how big it is. So theta 2 is 90 degrees. Third term is a little bit complex. So the third term, now you have to apply this rule in here. Okay. So you have the third term, theta 3 equal to inverse tan of b over a. So it's f over f naught divided by 1. So come back to f over f naught. Now the total term is basically theta 1 plus 0 plus theta 2 is 90 minus theta 3, inverse tan of f over f naught. So now we have the net phase of our transfer function is equal to 90 over inverse tan of f over f naught. So first of all, this is the only thing that probably is gonna confuse us. So let's study the behavior of inverse tan of x. So for inverse tan of x, if you have x equals 0, or in other words, if you have x go to 0, go towards 0, you have, what do I have here? If you have x equal to 0, you have the inverse tan equal to 0. But if you have x go to infinity, you actually have the inverse tan go to 90 degrees. So the value of inverse tan capped at 90 degrees. So here is our Bode plot. Okay. So we know that in this scenario, if the inverse tan is 0, it's going to be 90 degrees minus 0. So the total phase is 90 degrees, right? If the inverse tan is equal to infinity, if you go to 90 degrees, so 90 minus 90 equals 0. That's why we have this line here. How about at corner frequency? What's going to happen? So at corner frequency, which is this point right here, we have if the inverse tan, the inverse tan now become inverse tan of f naught over f naught, and f naught over f naught equal 1. So this whole chunk right here will go to 45 degrees. Okay, so the inverse tan of f naught over f naught equal 1 equal 45 degrees. So now you have this point here. How can we define the transition in this corner and this corner? So the easy way is So on the lower end, we just have the frequency to be 1/10 of the corner frequency, and on the higher end, we have the frequency of 10 times the corner frequency. So if you work on the same math, you would have the same thing for the low pass filter. So first, derive the expression for the magnitude of the transfer function. What I want to notice is, as you see, the k factor is basically the same, right? So we can see for the case of low pass filter, it allows signal to get transferred through here with a magnitude of k. One thing, in the same way, remember the high pass filter, the signal, basically the gain increase, then flat out, right? So higher frequency is allowed to pass through the filter, lower frequency is not allowed. And the transition happen at the corner frequency. So the low pass filter also happen in the same way. Low frequency is allowed to pass through, but high frequency is not. So you can have the Bode plot out as two lines like this. For the higher frequency segment of the plot, the gain decreased by 20 decibel per decade, and the transition happened at corner frequencies. Very similar to high pass filter. You just have to work out the math the same way. So for the phase component, it's pretty much the same with its counterpart high pass filter. But for the low pass filter, if you look at the phase equation in here, it's only difference by 90 degrees. So technically, the whole phase plot, you just have to shift it down by 90 degrees. So for a lower frequency, the phase is at 0, and for the higher frequency, the phase is at negative 90 degrees. Since we have been focusing more on the magnitude and the gain of amplifier, we have not considered the benefit of the phase in our transfer function. But when we get into the section of feedback amplifier, we will see the importance why we need to study phase component. And that's it for today. So if you have to, please review on complex number, because from now we will go through more in a lot of math in complex number. So I've already put a note in Canvas, so please take a look if you want. Next thing is, we have not actually go deep into derivation of transfer function, magnitude, and phase for the low pass filter. So it's very similar to high pass, but if you want some practice, you can do that still in your own time as a practice. So that's it.
This is the end of our lecture today. Thank you very much for watching the video so far. I hope you guys all learned something today. I'm very sorry for this. The quality of this lecture is not as good as others. I was a little bit sick the last couple days, and it's pretty difficult to try to keep up with all of this busy schedule. But I hope that this week I can catch up with our class schedule and produce video for you guys. So I'll see you guys next time. Bye.